Hello, I am Joe Bakhos, and I am here with the very first edition of the Taurus Report. It is called the Taurus Report for a not particularly profound reason. Basically, I am a Taurus, and this report is going to be about astrophysics and astronomy. And as we all know, astrology, astronomy, astrophysics, they're all the same thing. So, in any case, what I wanted to begin talking about is the recent results we're seeing from the Webb Telescope. Often in these reports, it may be referred to as the JWST, James Webb Space Telescope. And all the controversy that came out where many were saying that these results disproved the Big Bang. And so I wanted to delve into that, explore that a little bit, and give my opinion on this controversy. And so let us take a look at that. So the James Webb Telescope, in order to understand what the controversy is about, we need to understand redshifting. So basically the idea is this. Light takes a certain amount of time to travel. And so if we're looking at something very far away, like distant galaxies, it may take billions of years to get to us. So by the time it arrives to us, what we're looking at is not only very far away, but also we're getting a picture of it as it appeared billions of years ago. And so the further away something is, the further back in time we're looking. And so how do we know how far back in time something is? And we understand that by how much the light is redshifted. And so light is a wave, and by redshifting, all we mean is the light is kind of stretched out, so the wave is more stretched. And those colors appear redder to us, so we call it redshifting. When things appear sort of reddish, then we know that that light has been stretched. So I want to give an example here. Here's an example of what's called spectral analysis. And the basic idea here is whenever any element is burned, it gives off a certain characteristic light. Sodium, for example, when it's burned, it gives off a yellow light. And every type of star that we look at, it has its own signature, and it tells us what it is made of. And so we can classify stars based on their spectra. And here's an example of a spectra. These are emission lines from a certain star. And astrophysicists can look at it and they can tell what the star is made of and, what degree in its development it is and so on and so forth. Now, if the star is very far away and the light has taken a very long time to get to us, then this exact pattern will be shifted towards the red. Because, as I said, light appears redder when it gets stretched. And so when we see a star of a certain pattern, and we see that pattern shifted towards the red, then we can tell how long that light has taken to get to us, and we can tell how far away that light is. Now, what is interesting about the Webb telescope is that it is able to resolve red-shifted light to see galaxies that were so faint that no other telescope would be able to see them. And so we are, with the Webb telescope, able now to look further back in time than we ever have been able to do in the past. And so we're looking far enough back in time that we're getting near to the time of the theoretical Big Bang. And so if there was a Big Bang, there's certain types of things that we should be seeing, and we should be seeing the universe shaped in a certain way. And the Webb telescope is resolving things that are so distant and so far back that it can kind of look into that time period. And in the next segment, we will take a look at what it has found there. Now, the first thing I'd just like to note that I am going to provide in the comments links to all of the sites that I visit during this presentation. So, looking far back, what is it that Webb saw that's so controversial? So the idea is, if the universe started from a very hot, dense state, where all the matter in the universe was kind of compressed into some small space, and it's very hot, and then it expanded from that circumstance, we kind of roughly think of that general idea as the Big Bang. Now, recently, there's been sort of another controversy on exactly how we define the Big Bang and what those words mean, together with things like inflation and all of that, which I'm going to get into little by little to explain each step in the purported process about the beginning of the universe. But that is the basic idea, that early in the universe, all of the matter was in a much smaller area, it was much more dense, and it was hot. And it wasn't yet formed into things with structure like galaxies and stars. So you can think of it as a very compressed, hot, dense ball of plasma or gas. And then it expanded from that point. And as it expanded, it would take on structure, to first form like rough clumps of matter. And then from those clumps would start forming galaxies and stars and so forth. And so what is controversial about what Webb is seeing is that when you look back and you get near the Big Bang, we're not expecting to see galaxies and stars formed into neat spiral and disk galaxies like those we see in this modern time. When I say modern time, I mean things that are close to us, spiral and disk galaxies that we can see nearer our time. Instead, we're kind of expecting to see kind of rough clumps of matter, and not yet formed into those disks and ellipses. And this site at NASA gives an example of what we're talking about. So when Webb looked back, it did see lots of galaxies that are sort of modern looking. Okay, you've got spirals, you've got ellipses, you've got disks. And so we're seeing structure and galaxies at a time when we weren't really expecting that. Okay, and so this site, which again I will include the links in it, kind of gets into that and explains, why this is sort of unexpected. Now, a little later in the presentation, we will get into how astrophysicists are trying to interpret things in a way so as to preserve the Big Bang. But we'll get into that in the next segment. Another issue, another problem for Big Bang cosmology based on what we're seeing from Webb is the fact that Webb is seeing galaxies, not just the structure, spirals and disks, but it's also seeing galaxies that are smaller and brighter than what we expect. And the difficulty is this. Modern cosmology has incorporated a version of the expansion of space that Einstein suggested, which, if gravity is as depicted in Einstein's general relativity, an obvious question is, how is it that the universe is expanding? When we're looking at galaxies far away from us, and we see them extremely redshifted, which suggests that they're accelerating away from us, how is it that the universe can be expanding? Because, according to a very simple gravitational law based on general relativity, one would imagine that over time the universe would be compressing because of gravity. Gravity would be attracting everything and pulling it back together. And so Einstein introduced an expansion constant, and that has been refined by cosmologists over the decades. But the basic idea is that, according to this theory, space itself is stretching over time. Now, this stretch is very small on distances that we're used to, that we live and breathe in. So we're talking about intergalactic distances. At those distances, space itself is stretching. And so what does this have to do with the controversy with what we're seeing with Webb? And this part is sort of counterintuitive, but I'm going to link this article by Ethan Siegel it starts with a bang. This article's a few years old, but it's about this very issue that I'm about to talk about. And that is that if it is true that space itself is expanding, then something counterintuitive is going to happen when we look at very distant objects. Normally, when an object gets further away from us, we expect that object to appear smaller and smaller and smaller. And that is very intuitive, and that is a very normal occurrence to us. As an object gets further away, it's supposed to appear smaller. Now, if space is expanding, the counterintuitive thing that happens is at a certain far distance, and I forget what that distance is in the object. What is that? Well, in any case, the redshift is like near a redshift of 2. And I'll explain a little bit more about rating redshift later. But at a certain distance, that's very far away, so we're talking about billions of years light has been traveling to us. Once you get that far distance and you're getting near the time of the Big Bang, like that's how far back you're looking, as an object gets further, it does not get smaller. It instead actually starts to appear a little bit larger as it gets further away, if space is stretching in the way that modern cosmology presents it. Those galaxies should appear larger than they're appearing, and they should be fainter. Okay? So we have a problem in that Webb is seeing them smaller, as if they really are getting smaller with distance, and brighter. In other words, they're not fading. So what current theory predicts is that they will appear larger and fainter, and instead what we are seeing is that they are smaller and brighter. And this calls into question just the fundamental idea about space stretching. In other words, we may have to look at other explanations for the fact that light is redshifted from these galaxies. Now, that is incontrovertible. Okay, we know that the light is redshifted for the reasons that I explained a little earlier. And that redshift is explained by current theory based on the idea that space is stretching. Now, if space is not stretching, then we have to reinterpret that redshift, which I do in the theory which I am going to present later, reinterpretation of that redshift. But this is also something that has to be dealt with. This is also something we're seeing in Webb that current cosmology is having a difficult time explaining. Another issue that we need to deal with based on what we're seeing from Webb is metallicity. Now in this one I may be being a little premature in that a lot of studies about this haven't come out yet. So with that caveat that I may be a little premature, and this is one study I've seen that kind of illustrates what I'm talking about. This paper entitled "The Discovery of a Dusty Chemically Mature Companion to a Z4 starburst galaxy with Webb." Okay, and I'm predicting that we're going to see more papers like this, and that I am predicting that this metallicity will present even more of a problem as we look at more and more observations from Webb. So with that disclaimer that I may be a little premature on this, I'm going to proceed. And this is the basic idea. In the beginning of the universe, according to current theory, all that should be there is mostly like hydrogen and helium and maybe some lithium. But the point is, other elements shouldn't be there yet because stars make those by, they start at the beginning of the universe, it's theorized, of being just hydrogen and helium. And then they burn very bright. These are called population 3 stars. And they go supernova. And in the process of going supernova, that's when heavier elements are made. Now, on a periodic table, in the context we're talking about, basically anything beyond this hydrogen, helium, lithium, anything heavier than that, we're kind of calling metal. So we're using metal in a way that's not typically used day to day. Okay, basically we're saying anything, heavier than lithium, we're going to call a metal. And when I'm talking about metallicity, I mean the appearance of these heavier elements. According to current theory, these heavier elements only can be formed when stars go through a cycle of gas coming together. It forms a star made primarily hydrogen and helium. It goes nova. In that nova, heavier elements are made. Then it can go through another cycle where the gas comes together again and it goes nova again, creating even heavier elements. And so these heavier elements we'll call metals. We'll just lump them all together as metals. And so that's what we're talking about when we say metallicity. Now, this study in particular here, and I will link this again, it's showing that we have these kinds of metals present at this time. And here we have a Z equals 4, and that's the redshift. Z is the redshift. And I'm also going to link this redshift calculator that shows me when I enter a 4 in over here, and then just press flat because we're in a flat universe. It will tell us that this is the universe was about 1.5 billion years old at the time. Our sun is 4 billion years old. And so this is like right at the beginning of the universe. And back then we're kind of expecting mainly to see population 3 stars, meaning just hydrogen and helium only, without any metals. And here we're viewing light that shows that these metals are present. And how do we know they're present? It gets back to this first thing I talked about, was these spectral signatures. Remember where I said that when you analyze light, every element when it's burned, or I should say heated rather than burned, but anyways, any element when it's heated, it gives off light with a certain signature. So that is how we can tell what stars are made of, because we're seeing the signature, or at least in this study, they saw the signature of metals being present. And this does present another problem, because supposedly near the Big Bang, metals shouldn't be present yet because a star's got to burn for 1 billion years, and then reform, and then go nova again. And so at that time, according to current cosmology, there wouldn't have been time for that. So metallicity does present another problem. Very good. So now I'd like to take a look at the controversy about all this. Big name in this controversy when it first erupted was Eric Lerner, who has his own theory called plasma cosmology. And I would just like to show you something. If we were to go into Google here, and I am going to put quotations around Eric Lerner, and then I'll do JWST, and then I'll put quotations around Big Bang, and I hit enter, and we start seeing the controversy. Many cosmologists coming in to basically argue against what Eric Lerner was saying. I have a little difficulty in this sense. As I scroll down here, most of these links, if you click on them, will be people explaining why Eric Lerner is wrong and why the Webb telescope did not disprove the Big Bang. Basically, I think kind of presenting him as a crackpot, and doing all of that. And here's my difficulty with this. To me, there's two separate issues. There is Eric Lerner's own theory, plasma cosmology, which I am not going to get into critiquing that theory because I have my own theory to present. And so I'm not really going to discuss plasma cosmology, but I do suggest, if you'd like to really see some of the intimate details of this controversy, you might want to Google that and look into it and see what Eric Lerner has to say rather than having me present his stuff to you. But here's the difficulty I have with the mainstream response. The valid points that Eric Lerner raises are the ones that I have already presented to you thus far. Okay, those three main issues. Okay, number one, seeing disks and spirals that early. Okay, number two, seeing galaxies so bright and so small that early. Okay, and number three, the metallicity. Okay, now these issues are valid and they present a real challenge to mainstream cosmology. And in all of these articles, when I click on them and people are arguing about Eric Lerner and what he said, what they do is they launch into attacks on his plasma cosmology and they skip over all of the valid critiques. And thus far, I have not found any satisfactory mainstream response to any of the objections raised by Lerner. And I feel that we should sort of bracket and kind of set aside debate about plasma cosmology and let that stand or fall on its own merits. But setting that aside, why not address the very real and valid objections that Lerner raised, which I happen to agree with. Now, I do notice the only real mainstream article I found that in a well-respected journal was this article by the Scientific American, and I was greatly relieved when I saw this. The Scientific American, it said Webb is breaking the Big Bang paradigm. Okay, and here this article is basically saying what Lerner said is that this presents some real challenges to mainstream cosmology, And I am not seeing them address those. Now, in their defense, like good scientists, they want to wait for the data and analyze that. And so I think many cosmologists and astrophysicists at this point in time, they're saying, I don't know, which is an acceptable thing to say. But I guess I would like to see more open acknowledgement that the Big Bang paradigm has some real difficulties to answer. And I'll delve into that a little bit in the next segment. Mainstream cosmology, which is really general relativity, lambda, cold dark matter theory, along with, that's probably like 90% of modern astrophysicists subscribe to that theory. And also there is MOND, modified gravity, originated by Mordechai Milgram. And they are probably the other 10% of modern cosmologists. What all of them have in common is a belief in the Big Bang and a belief in interpreting cosmological expansion as the stretching of space itself. Now, in order to save standard cosmology, I'll call it, after seeing the results from Webb, they have to play with different things like the expansion rate. They can play with it so that these galaxies had time to form. They can play with gravity so that these galaxies would have time to form. They could play with dark matter and putting it in different places, different shapes and densities of dark matter. They could play with the idea of black holes. I've seen some papers attempting to do that. So there's various ways to kind of play with all of these parameters to make the Big Bang and stretching of space consistent with what we're seeing from Webb. I am skeptical of that, and I am going to present my own theory, which is cyclic gravity in cosmology, CGC. And CGC, it presents a universe that is eternal and forever alternating between periods of gentle, I call it gentle like it's not an explosion or not a rapid expansion like Big Bang. It's a gentle expansion and gentle contraction. And this theory does this without dark matter, without dark energy, without the stretching of space, without things like inflation, and using only those forces that we are very familiar with. Okay, just the basic forces, the strong, that particle physicists have been working with for decades. The strong force, the weak nuclear force, and electromagnetism. So just using those forces is able to present this cosmology. Now, the criticism of any type of proposal like this is based on, well, I shouldn't say that. A major portion of the criticism is caused by two phenomena that we observe that would challenge any theorist to come up with an explanation with them, different than the Big Bang and cosmological expansion. And that is the redshifting of light. We see that light is redshifted all around the universe, and any theory has to explain that. And we have the CMB, the cosmic microwave background radiation, which standard theory explains as the afterglow of the Big Bang. So any theory seeking to supplant Big Bang cosmology is going to have to explain the CMB. Those are the two major things. The the cosmic microwave background radiation, and also the redshift that we're seeing. So in my next episode, which will be next Sunday, let's see, what are we on? We are on November 27th, so that will be December 4th, sometime in the evening. And I live in California, so when I say evening, I mean California time. I will post the next episode in this series. And in that episode, I want to delve into a little bit an explanation of the cosmic microwave background radiation and cosmological expansion, understood by standard theory as the stretching of space. And I'm going to propose alternative explanations to those before I get into, in the episodes following that one, a in-depth, step-by-step explanation of my theory. Thank you very much for watching, and we will see you in a week.